So just let me, if you don't have a question, basically I'm gonna emphasize again, in all reactions that alcohol serve as a nucleophile, okay, the reaction always happens between the oxygen atom with whatever electrophilic atom you have on the other side, okay? So depend on, there's a bunch of electrophilic atoms, you know, you might encounter. Something we have seen it in, you know, organic one, like thionyl chloride, okay? So in this thing, the first step is the nucleophilic oxygen attack sulfur, okay? And then this attack eventually, you know, if you really look at, I'm going to show you the full mechanism. So something like this, okay? If it attacks here, and then certainly you're going to form sulfur will become SO single bond. This is going to give you the this guy, okay? Where's the extra electron? Oh, extra pair. Yeah. Okay. Yeah, that's correct. Okay, extra pair. Okay. So then the next thing is usually this reaction can use some kind of organic base. Okay, and this organic base could be just pyridine, and this pyridine has a lone pair. Take the proton away. Plus this protonated pyridine. Okay. And then what happens is the SO double bond want to reform, then push the chloride away. See this type of mechanism, you're gonna see quite a few times in the organic tool. So the basically what you see is the first it's more, you're gonna see more often with carbonyl group, but sulfur has very similar electron activity as carbon. So SO double bond often behave as the CO double bond similar. Okay. So but what you see is first SO double bond gets open, then the SO double bond restores, push the chloride away, and then the chloride, okay, and if you recall what we learned in organic one is reasonably good nucleophile and ionic, and this whole thing, okay, this whole thing is actually a very good living group. This whole thing is a very good living group, just like the tosylate. So what happens is the chloride can attack this electrophilic carbon from opposite side of living group, and then these things come to here, and actually I should say directly, this thing directly come to here, okay, and then this one leaves, become the the SO2 and the chloride. So this attack is SN2 type attack. So you will see a configuration inversion here. Okay, so basically we'll see all because the configuration inverted. So we're gonna see chloride here, hydrogen here. Okay, and the plus SO2 under the chloride ion. So that's something if alcohol react with thionyl chloride. We actually see this reaction organic 1. Here, just go through the mechanism again, and some details you probably haven't seen organic 1, like involving the addition of the SO double bond, then restoration of SO double bond. This is very similar to the carbonyl group you are seeing. Okay? Now, more commonly, you will see electrophile like, say, if you have the same alcohol, if you react with TSCl, what is TSCl? Is this thing. This is TSCl. Okay. So again, the reaction will start. The nucleophilic oxygen atom attacks electrophilic atom here, which is sulfur. Okay. And then this one, basic on addition give you this product. So SO double bond gets open. I don't want to here. I say I want to keep the configuration, so it's easier to draw like this way. Okay. So this one connect to the this, okay, and obviously this is gonna be a positive charge. So then you will have a pyridine taking the proton away again. Taking this proton away. So you're gonna have this chloride, okay? And the next thing is SO double bond want to restore itself. So because SO sulfur is very oxyphilic, love to bond with oxygen, even more than carbon does. So sulfur and phosphorus both are very oxyphilic atoms. So what you see is TS, okay? And the TS is equal to plus the chloride, okay? Here, chloride. Basically, what you see is because of this reaction only involves one-step nucleophilic attack of the hydroxy oxygen to the electrophile. So the configuration of the alcohol is completely retained in the product. Again, we have seen this in organic 1. So how the sulfonic chloride can convert the bad leading group of OH group to an excellent leading group of positive. And the configuration of the chiroidal center in the alcohol is completely retained because of this chiroidal center did not involve in the entire reaction. We have seen this, this process in organic 1, but hopefully now you have better understanding. So by seeing the mechanism, so the alcohol attacks the electrophilic sulfur atom in sulfonic chloride, and SO double bond gets open, then they become SO single bond, then the SO double bond would like to restore itself, then push a chloride away. Why they want to restore itself? Because the SO double bond is really stable bond, just like a CO double bond. You're gonna see this kind of example also, okay? Now, next example is, again, we have the same alcohol. if we let it react with, say, random, this guy, okay? So if you look at this compound, okay, we have seen this compound in chapter 13. It features extremely electrophilic carbon here because of, this carbon is on the dual electron withdrawing effect from both carbonyl oxygen and the chlorine bound to the carbon. So this carbon is very, very electrophilic, okay? So if you want to understand this reaction, basically, okay, you understand the oxygen will be attacking here, okay? Then we'll form this, the CO double bond will be open, become CO single bond. The detailed mechanism, we're gonna see many times. This type of mechanism, you will see many times over the course of organic tools. So please be familiar with this. In chapter 15, we already saw that the Grignard reagent does this, okay? But we will see this many times, okay? So the difference between acyl chloride or ketone or aldehyde is that this chloride, okay, is an extremely good leaving group. We have seen in organic 1, it's very good leaving group, okay? So that's why the reaction did not stop at just the addition step, okay? So if you get this, and the reaction also often involve a base, like a pyridine. And the pyridine's role actually could be more complicated than what I'm showing here. But just for the sake of simplicity, at this point, we just understand it as pyridine because the base gonna serve the role of taking the proton away. Okay, but in chapter 20, we will see that the pyridine actually serves a role more than just taking a proton away. Okay? But at this point, we assume that just does this, just for the sake of simplicity. Okay? So then this will give you the so you see, let me put this way. At this point, I want you to have a feeling of how this reaction will work. Okay, I'm not asking you to know every step of mechanism because that's a requirement for let's say chapter 20, something like that. Okay, but here you have a feeling. Okay, they get used to the reaction style. Okay, there's a nucleophile attack the carbonyl carbon. That's addition reaction opens the CO double bond, okay? And then the CO double bond, because it's very strong bond, want to restore itself if the condition allows. So what do I mean when we say if the condition allows? Is that the means that if the restoration of the carbonyl group will not generate a horrible leaving group. That's usually what means that the condition allows. Okay, so now what you see is now you have the CO single bond here. So what happens if the carbonyl group restores itself? What kind of leaving group we are generating? Is the leaving group a horrible leaving group? Chloride ion? No, it's like a very good leaving group because hydrogen chloride is a very strong acid, and this chloride ion is very weak base. It's a very good leaving group, so there's no problem generating the restoring the carbonyl group. So what you see is then you will see, okay, so the requirement for your to answer the question you expect in next exam is what you see is this CO bond, okay, this CO bond or this carbon never involved at any of those steps. This carbon never involved in reaction. Okay, that's why configuration. If you have any chiral center in the alcohol, the configuration will be completely retained in the product. No change whatsoever. Okay, no change whatsoever. I'm not asking you to know the entire mechanism, but I would like to you have a develop a feeling about it. Okay, so that we can use it in later chapters. At this point, I'm not going to require you to know, oh, which one's rate limiting step was. So rate limiting step usually is a attack to the carbonyl group, but it's not required at this point. Okay. And just probably last example of this type of reaction, I'm going to use the same alcohol again, chiral alcohol. And this time, I'm going to react with this. Again, we have, say, some period in there, okay? So the alcohol will be the nucleophile. So which atom will be attacking? Which atom will be attacking? The carbonyl carbon, always, okay? That's the most electrophilic atom we have here, okay? So then this will be, okay. Again, this just I'm helping understanding what kind of product we will be getting. The exact mechanism actually will be different. Exact mechanism. When we go into chapter 20, we have more discussion about. But at this stage, I just give you a general aspect. Is the OH group of the alcohol with oxygen serve as the nucleophilic atom will be attacking the electrophilic carbonyl carbon. So this will give you this guy OH okay. Then you probably can guess period in here serves organic base, takes the proton away, taking care of the positive charge, the proton, on the original alcohol oxygen. Now, you need to answer the question whether we can restore the carbonyl group, okay? So if you think about restoring carbonyl group, okay, then one of the bonds on this carbon needs to break. So obviously, you don't want to break this bond because it will create a very, very impossible leaving group, okay? If you break this bond, go back to the starting material, no change, okay? So what about breaking this bond? Okay, this bond gives you a carboxylate ion. Is it a bad leaving group? Well, you have to compare it with OH minus. Carboxylate is about 10 orders. Carboxylate ion is about 10 orders magnitude less basic than OH minus, about 10. So it's a much better leaving group than OH minus. May not be the best leaving group you can have, like chloride, water, bromide. Those are excellent leaving groups. But consider they are reasonable good leaving group. Reasonable, modest good leaving group. Not great, but modest good leaving group. So yes, it can form. So that leave you the product. Okay, the products. Okay, so basically. Carbonyl restores and carboxylate. Oh, carboxylate breaks off. So what you can see, the reaction is actually similar to the reaction of those carbonyl involved compounds when they serve the electrophile is similar what we learned in chapter 13. In chapter 13, I hope you recall, when this guy serve as a Friedel electrifying Friedel-Crafts acylation reaction. This one is actually electrified with carbonyl carbon bound to the aromatic ring. Okay, and this entire part, okay, will break off, in the reaction into another product, give you a carboxylic acid. Same thing here. You see the electrified side, okay, will be bound to the oxygen of the alcohol, and the green part, okay, come off as another organic product. Okay? Same thing, okay. And the acyl chloride, when the serve as electrifier, you see this entire electrophilic part, this part, okay, will be bound to the carbonyl oxygen, okay, and the chloride ion will break off. So this is the electrophilic part, okay, bound to the the alkoxy part of alcohol. And the key part is alcohol. Any configuration, catalytic center you might have in the alcohol will be completely retained in the product. Any questions you might have? And the thiols, they are about 6 orders of magnitude more acidic than alcohol. That's probably last section of the things you're supposed to cover. You're supposed to watch. Why thiols are more acidic than alcohols? We actually discussed in organic 1. Why thiols, if are the same, okay? Thiols is about 1 million times more acidic than alcohols. Why? Because you see the key bonding, we are looking at OH bond, SH bond. The S is bigger, so SH bond is substantially longer, easier to break, to make it more acidic. And S and O, they are in the same group. Okay, so electronegativity, yeah, we know S is sizably less electronegative than O, but S is still substantially more electronegative than H. So that's why thiols is substantially more acidic than alcohol. And the most relevant reaction you might see in future is the conjugate base of thiol is one of the best nucleophile you can have in the reaction. One of the best nucleophile. It is about 100 times more nucleophilic than alkoxide. And alkoxide itself already very good nucleophile. Sounds about 100 times better. And what is more important in practical reactions, if you want to carry out SN2 reaction, yes, if you learn, you should recall how we learn organic 1, when you have an ion nucleophile carry out the potential reaction with the alkyl halide, you always have to think about the possibility of elimination to compete with SN2. And the likelihood of to see elimination is strongly associated with the basicity with nucleophile, because thiolate is about 1 million times less basic than alkoxide, and it's about 100 times more nucleophilic than alkoxide. So thiolate, when it reacts with secondary alkyl halide, you will have mainly SN2 product, okay, not E2. While alkoxide, you will have mainly E2 product. That's the difference. You have learning organic 1, but we'll be revisiting organic 2. So if it's secondary halide, alkoxide will have E2 as a major product, but thiolate will SN2 have the major product. Okay, primary both gonna have SN2 as a major product. Okay, I'm gonna just stop here. I'm gonna see you guys next class. I guess Monday. Yeah. And today, right?